In this demonstration, you'll learn how to set up a modal structural simulation to study the results of vibrations and mode shapes on a circular plate. I'll start by selecting a simulation process template from the study panel on the left. I'm going to select the structural template. I'll select the option to define new geometry. I am running a pure structural simulation, so I won't select another physics type. I can either do a static analysis or a modal one. For this example, I'll select a modal analysis and accept the default selection for the options list. Typically, automatic contact detection is performed. AIM has automatically created the physics solution process using default settings for the geometry, meshing, physics, and results. Here's a summary of all of the tasks, along with their status. These tasks are also available in the workflow window in a data flow diagram format. In creating my simulation process, the first thing that I'm asked to do is define my geometry, so I'll select the geometry task. There, I'll choose to import a geometry file. I'll select the geometry for the simple circular plate, a very common geometry used to demonstrate modal analysis. You can see that the geometry task has a green check mark, indicating that the geometry file was properly uploaded. The meshing task has a yellow lightning symbol, which means it's ready to update. It has all of the information it needs to produce the mesh, so I don't need to edit anything here. The first thing we need to do is add a support, which we do in the physics solution task. I'll click on physics in the workflow view to go into the physics solution task. You'll see that a lot of defaults have already been set up for me: material assignments, physics options, and solver options. If we take a look at the default solver settings for this analysis, we can see that we are requesting 6 eigenvalues by default. Now I'm going to add a fixed support to the 2 faces of the plate, which makes the plate fully clamped at the ends. I'll first use the face selection filter to select the faces on the sides of the plate. Then I'll add the support boundary condition from the context menu. The support boundary condition is now up to date, and my physics solution is all set up. I'll solve this physics solution now. Because the meshing task was also ready to go, it will be automatically updated first. I can see the progress on the bottom right-hand side here. Once the meshing task is updated, AIM will move on to the physics solution task. This simulation is now solved, so we can look at the resulting eigenvalues here on the output of the physics solution panel. You can see that we have the 6 modes generated by default. Now I can view my results. I'll click on the results task. I want to add the modes and animate them. I'll add a displacement magnitude contour result. I want the results for mode 1. Then I can evaluate to view the mode shape for this mode. Right-click, and I can animate the displacement. I can view the animated displacement results for all of the modes. This concludes this demonstration of an end-to-end basic modal structural analysis in AIM.